Greetings all, and welcome to this very first conversational science video. Now, because this is the very first of these videos, let's lower our expectations a little and start with a relatively simple problem. What is the average speed of a nitrogen molecule in the air at room temperature? Temperature is a way to measure the average kinetic energy of the particles in whatever material you're looking at. And what does that mean? Well, we'll talk more about kinetic energy in a future video if I ever actually finish a future video. For right now, in the air around me, the air molecules are flying around, bouncing off each other, bouncing off of me, bouncing off the walls. The faster the air molecules are moving, the warmer the air temperature. If the air molecules are moving more slowly, that's a cooler air temperature. We have two equations we can use to approach kinetic energy using algebra. Our first equation is kinetic energy is equal to 1/2 mv squared, where m is the mass of the nitrogen molecule and v is the average speed of the nitrogen molecules. Why is it v for speed? Well, it's actually v for velocity. There's a technical difference between velocity and speed that we can worry about later if you want to talk about vectors and scalars, but for right now, I don't care about the direction the nitrogen molecules are going, I just care about their average speed. Our second equation for kinetic energy is from our old friend, the dead guy, Dr. Boltzmann. Kinetic energy is equal to 3/2 k sub b, which is the Boltzmann constant, times T, and T is the temperature on an absolute temperature scale. In degrees Celsius or degrees Fahrenheit, I can have positive numbers, I can have negative numbers. That makes my equations more complicated. On an absolute temperature scale, 0 is absolute zero, which is the temperature at which the particles do not move at all. So on an absolute temperature scale, I only get 0 at absolute zero, and by the way, we can't get to absolute zero. At any other temperature, it's a positive number. I only have positive numbers on an absolute temperature scale. That makes my arithmetic easier. I like easier. So I can set those two equations equal to each other. 1/2 mv squared equal to 3/2 k sub bt, and then we do our algebra tricks to solve for v. So I can cancel the 2's. I can divide both sides by m to move the mass to the other side of the equal sign. I have v squared all by itself on the left. I take the square root of everything. I end up with v is equal to the square root of the quantity, 3 k sub bt over m. Very well, my next part of the problem is what is the mass of a nitrogen molecule? So from the periodic table, a nitrogen atom has a molar mass of 14.007 grams per mole. Nitrogen molecules are actually each two nitrogen atoms covalently bonded to each other. So the molar mass for nitrogen molecules is 28.014 grams per mole. In a few seconds, I'm going to want to have that mass in kilograms instead of grams so that my units cancel correctly. So I throw in a conversion factor. 1 kilogram is 1,000 grams. Then we multiply by our other old friend, the Avogadro constant. 1 mole is 6.02214,076 times 10 to the 23rd, in this case 10 to the 23rd nitrogen molecules. The grams cancel, the moles cancel. I end up with kilograms. I crank through the numbers on my calculator. 4.6518 times 10 to the minus 26th kilogram per nitrogen molecule. Now 10 to the minus 26th is a very small number, but keep in mind nitrogen molecules are very small things. Now I can take that number and plug it into our previous equation. V is equal to the square root of 3 times the Boltzmann constant, which is 1.380649 times 10 to the minus 23rd kilogram meter squared per Kelvin second squared, times the room temperature, 298 Kelvin. The kelvins cancel, divided by the mass of the nitrogen molecule, 4.6518 times 10 to the minus 26th kilograms. Now the kilograms cancel. The only units I have left are meter squared and second squared under the square root symbol. So my answer is 515 meters per second. Now for those of us here in the United States where we only use the metric system at gunpoint, 515 meters per second is roughly 1,150 miles per hour. So as I'm sitting here, the nitrogen molecules in the air around me are bouncing off of me at more than 1,000 miles per hour, which is pretty impressive. Do you want to talk about significant figures? We can talk about significant figures. Let's talk about significant figures later. For our very first video then, the average speed of a nitrogen molecule in the air at room temperature is about 515 meters per second. If I ever finish a second one of these videos, I will see you there. Thank you.